Hi and welcome to video 1 on this series on vectors and vector notation, Unit 1, Topic 2 of the Specialist Maths curriculum. And in this video I'm going to take you through my OneNote on the initial vectors component of the course. So the assumption here is that you haven't really seen vectors before at all. Now it's a fairly simple concept and it should hopefully make a bit of sense around why we do it, but there is some really good context to help you build into this an understanding of why and what we're doing. But let's start with the most common one, which is kinematics, and you will have seen this in science and math methods before probably. But basically we have two different things to measure length. So we have distance and we have displacement, and there's a difference between them. So in short and verbally, the distance I travel does not have anything to do with direction. So if I take a step forward, say a metre step forward, and a metre step back, then I've travelled 2 metres, and that's a distance. My displacement though would be a metre forward and a metre back would give me a displacement of 0 because I've technically not moved from where I started. So that's like an overall position based on where I started. Because I've got a positive 1 step forward, but then a negative step back, and 1 plus negative 1 is 0. So that means that where distance is a scalar product, displacement is a vector product. And speed is associated to distance, and velocity is associated to displacement, and acceleration kind of relates to both. So remember, speed and velocity are a measure of change of distance or displacement, and acceleration is the rate of change of velocity or speed. So if you change your velocity, then you are accelerating or decelerating. So let's talk about vectors. A vector is a quantity that has both magnitude and direction. The magnitude is the distance bit of displacement, but then the direction is it positive or negative? Or in a two-dimensional plane, say for example, are you going north or south or east or west or some other variant of that? A scalar has only magnitude, so we only care about the actual distance travelled, not the direction. And there's the examples we just talked about. Let's talk about how we represent vectors. So item 1 there, this is the most common representation of a vector that you'll see, and that is if we start at point A and go to point B, well that is represented as vector X. So you'll see there's an arrow on there, so we're going from A to B, and this could also be written as A to B like that, with an arrow on it. Because it's a vector and not a scalar, we have to represent that, and that's where this little squiggly line comes in. And so you'll see that, or maybe you'll see this arrow on top of a starting and finishing position. Mind you, we could write this as BA with the arrow going backwards, that would be the same thing. And it's important to recognise here that BA, so to get from B to A, that's equal to negative A to B. So that is the same distance but in the opposite direction, so it's negative. In a textbook or maybe in an exam or online, you'll probably find that a vector is represented as just a bolded letter. So X unbolded is just a variable or a letter being used, whereas if it's bolded it probably represents a vector. But you've got to look at the context as well. Number 2 is where we can set it up as basically a coordinate on a Cartesian plane. So that 3, 4 vector there, commonly represented vertically, but sometimes represented horizontally, although that looks a little bit too much like a coordinate, which is why it's usually vertical. The 3, 4 represents a 3 horizontal, 4 vertical. Now, the important thing about 2 is it leads into 3, this red section here. Now 3 is not a part of Unit 1 necessarily, but it's still an important feature of what you'll do because it comes in Unit 3, and that is component form, where we have I is equal to what we call the unit vector in the horizontal direction, so 1 across, 0 up or down, and J is what we call the unit vector in the vertical direction, so 0 across but 1 up, and we can represent any vector as a series of I's and J's. So if we go 3 across and 4 up, then this is 3i plus 4j. If we go 3 across and 4 down, it would be 3i minus 4j. So we have got the component form as well. So there's the different forms. So now let's talk about vector arithmetic, which works exactly as you would expect. When I add x and y, I get basically the addition of my horizontal components and the addition of my vertical components. But let's have a look at what happens when we sketch them and how that looks. So if I sketch, my apologies, x, I'll just zoom out a little bit, is 3, 2. So if I go along 3 and up 2, then x is approximately here. And so the vector is this. And I'll change colours now to show you why. Y is -1, 7, and that is about here on my scale. And so this looks like that value there. There's my x and y. If I add x and y together, x plus y gives me 3 plus -1. So x plus y is 2, because that's 3 plus -1. And 2 plus 7 is 9. And 2, 9 is, again, different colour. 2 along, 9 up is here. And this is my vector x plus y. And hopefully you can see there's some nice little patterns going on here. First of all, if I do a bit of connecting, it creates this parallelogram, which is kind of makes sense because we're moving x, and then this is vector y as well. So x plus y takes us from our starting point there, which I'll call O, to our outer point C. We'll call this B and A just to give us some naming points. O is the centre of our diagram, it's the origin of this Cartesian plane, and C is out there. At the moment it's at the coordinate 2, 9, and x plus y is that vector from O to C. Now vectors aren't transferable on a plane, and it depends a bit on context here, but the ones we use in maths will be pretty much transferable. So what I mean by that is, we've got vector y here and we've got vector y there. The vectors are exactly the same, O to B and A to C, just one's been transferred to a different situation or a different placement, different beginning location. But you'll see the vectors, for all intents and purposes, what they mean are the distance and direction from some point to another point. So they'll just be the same length and in the same direction, we get equivalent vectors. So like that and that. And scalar multiplication. So calculating these, 3 times x is just 3 times, keep in mind x was 3, 2, and that's equal to 9, 6. So 3, 2, which is here, just blows out to be 9, 6, which should be just further along here. This is 3x, because this is x, and this is x, and this is x. You'll notice here that a scalar multiple doesn't change the direction, but it does change the length. Multiplies it by a factor of 3 to make the vector 3 times longer. And that's all that happens. That's what it looks like on a Cartesian plane. And also the actual arithmetic here is fairly simple, as you'd expect. -2y, same thing. Our previous y was up to here. -2y will be negative, so in the other direction, and twice as long. It's going to take me right down into our other stuff, but hopefully you can see the point there. And then of course we can do a linear combination of x and y. 3x minus 2y will be 3x here, and then minus 2y will be down here somewhere, and that will be our resultant vector out to there. So remember, this is our 3x minus 2y. Obviously be a little bit more accurate than that.